Well, thank you for coming. And this is Chris's professional, professional science master program. It's a relatively new graduate program in our department. So my name is Yang Dong Pan. I'm a professor of environmental science and management at PSU. And I'm one of Chris's 3 committee members. So other 2 committee members include Dr. Eugene Foster from Oregon DEQ. And Gene is also an affiliated member in our department. He teaches several courses there. And we also have Ron Willinger from Clackamas West. So Ron is our community partner. Okay. So you all know Chris. Chris starts his undergraduate education from Low Columbia College. And he earned his bachelor degree in chemistry from Western Washington University, I think it's 2010. Then he started to work for WES, and in 2019, he joined our program at PSU. And it's very unfortunate because quickly, once Chris joined our program, the COVID starts. Okay. So it has been very, very difficult journey for everyone, including Chris, especially he has also have a job. And so it is remarkable for him to come to today, to share his research with everyone. Okay. So before we let him take over, let me see a little bit about this professional science master degree. Okay. So this is a very unique graduate program, because in addition to those coursework in science, in ecology, in physical aspect of environmental systems, we also require students in their program to take some additional courses like communication, like project management, and environmental law and regulations. So with that kind of a combination, we hope students can, once they get a degree, they can readily just become a very important part of the professional field. Okay, so the final component of this program is to do a research project with the community partners' support. So in this case, this is great because Chris works for WES, and he has the full support from WES and all the logistic support. Plus, there's such a nice system to construct wetland, and which Chris is going to talk about. Okay. Well, the way we're going to run this presentation is like that. Chris is going to give his talk. Okay. After that, we're going to open up for questions. So we have a question from the live audience. Also, we can have a question from our audience remotely. Okay. Then after that, we're going to take a quick break. Okay. So after break, we're going to come back, just Chris and his committee members. So his committee members can ask some more friendly questions. And so then after that, and the committee is going to make a recommendation about Chris's degree program. Okay. So now, without further ado, well, here you go, Chris.
Hi, everyone. Thank you all for being here today, and thank you, Dr. Pan, for that introduction. My name is Chris Desiderati, as Dr. Pan said. I have worked for WES for about 7 years. Like he said, I started grad school about 3 years ago, and I'm going to talk today about the Carli Creek constructed wetland that WES built also, I guess, about 4 or 5 years ago. So next slide, please. So first thing I want to go over is my community partner. Dr. Pan was introducing earlier, Water Environment Services is a community agency that kind of has 2 main roles in its mission. One is sanitary sewer services. They have hundreds of miles of sewer pipe under the ground, lots of pumps. And the other part of their mission is surface water management, and that includes a lot of monitoring. It includes building certain ponds and stormwater treatment systems, as well as constructing this specific wetland, which was a part of my project. Next slide, please. So what is my project about? And why is it kind of important? So the main takeaway is that urban stormwater runoff is a point source pollution problem. And when I say point source, what I mean is stormwater pollution that is conveyed through a pipe into a stream. So if anyone here is from Portland, and I don't see many folks that may be from Portland, but if you are, you may be familiar with what's called a combined sewer system, where sanitary sewer waste from toilets and sinks and stormwater combine underground into the same pipe and get treated at a wastewater treatment plant. What we have out here in Clackamas County is a little bit different. It's called a separate storm sewer system, where stormwater that comes from the sky, obviously, and falls on rooftops or parking lots, flows to its own set of pipes and gets discharged directly to a stream. The stuff from toilets and sinks, that goes directly to a wastewater treatment plant. So that direct to the stream part is important and is relevant to why this constructed wetland was built and its purpose. So next slide, please. So urban stormwater runoff, pollution, bad. What do managers typically, what approaches do they take when they're trying to treat this stormwater? And one way to think about it is on this gray-green infrastructure continuum. And gray and green refer to the colors of the infrastructure itself. So gray is referring to like concrete, pumps, pipes. Green is referring to sort of more natural areas, ponds that collect stormwater and treat it through settling and other physical processes. So where does this constructed wetland fall in the spectrum? It's more towards the green side, and that red box shows it's more of a stormwater wetland, a constructed wetland and a pond. So next slide, please. So what are constructed wetlands? I'm going to use that term a lot. They're systems that use sunlight and gravity to treat stormwater runoff. There's no electricity running to them. They provide a lot of ecosystem services, which, if you're not familiar with what that is, it's a service the environment provides to people if it's functioning and healthy. So a couple different categories of ecosystem services are things like water quality treatment and improvement, which is what I'll talk about today, as well as some cultural services such as education, which is kind of what's going on today in this room, or cultural and habitat provisioning resources. So, you know, birds can go and spend time in these constructed wetlands, or fish can live in them sometimes. And how they work are really, there's three main categories of processes. I'll get into this a little bit later when we get to the data, but there's physical, chemical, which are things like co-precipitation of metals with certain compounds in stormwater. And then there's biological processes, such as nitrogen being absorbed into a plant to help it grow. Next slide. All right, let's get to the wetland. So about 10 or 9 years ago, Wes approached the Carli family, which owned some farmland right on the banks of the Clackamas River next to a very industrialized area, and acquired the Carli family's farm property. After they did that, they began designing this $3.5 million kind of marquee project, which is the constructed wetland. And the project had three main goals. The first goal was to catch the stormwater in this catchment. And catchment's a fancy word for the area that collects stormwater and then discharges it to a certain point. So one of the project goals was to catch all this water and help treat it through this constructed wetland. The second goal was to restore some of the stream. Carli Creek had been getting, hammered for years. There had been, there was a lot of data to prove that it was not a great looking stream. And then the third goal for the project was to integrate this constructed wetland system into the restoration process as a way to help treat stormwater pollution. Like it says up there, tens of thousands of plants were planted around the area, as well as a lot of large wood. Next slide, please. All right, so let's get a bird's eye view of the constructed wetland. I want to walk you guys through how the water moves through this system. So now we're looking at an aerial view over the constructed wetland, and the white dashed dot is the flow of the water through the wetland. So it starts coming out of a pipe of the separate storm sewer system I was talking about earlier. It falls down these step pools, which help lower the elevation and dissipate energy from the water because it comes out pretty fast. And then it hits this half-acre retention pond. And the retention pond begins the treatment process. It allows the water to kind of sponge into the system and accumulate and start settling out things that are suspended in the water. After that, it goes through a structure that restricts the flow, so not too much water goes to the bioretention cells. And the bioretention cells are next, which is a combination of traditional wetlands that you'd think of that hold water and allow specific wetland plants to grow. And then a very similar kind of wetland that allows water to infiltrate through the ground and absorb into the ground. And those bioretention cells and that detention pond make the treatment terrace, which is a term I'll use a lot in this presentation. After that, the water flows over log weir into the backwater channel, which is hydrologically connected to Carli Creek itself. That water then flows to the Clackamas River. Next slide. So I want to talk about a conceptual model to think of how pollution gets generated and where it goes. So if we start again in the sky with rain falling down onto hard surfaces or impervious surfaces, as well as pervious surfaces. And when they hit these hard surfaces, they pick up these pollutants that are shown up there in the circles. Different categories of pollutants I have shown there, like nitrogen or metals. And those pollutants are transferred to the separate storm sewer system. And then once in there, they can either go to the Carli Creek itself, which helps form some of the flow in the creek, or it can go to the constructed wetland, which is in that green box. The constructed wetland has three main units, as I described already, and those italicized words next to them are just some hypothesized mechanisms that help treat the pollution in those different units in the system. Next slide. So why should you guys care about this constructed wetland or this system in particular? I know some of you are here just because you know me, but it's also cool to think about this wetland because it's a very young wetland in terms of it only having been planted about 3 years ago. It has a lot of time to mature, and it's good to get a baseline look at how this system performs now. So if we want to study it in the future, we'll have some context to look at. There's also some regulatory compliance reasons in terms of WES having an MS4 permit with the state for its separate storm sewer system. WES is in charge of maintaining it and determining any effects it may have on local streams. And adaptive management is another reason, which is like a fancy term for taking steps to restore the environment in the face of uncertainty. This constructed wetland is intensely utilized. For every 1 acre of constructed wetland, there's 243 acres of catchment. So anything that happens in the catchment is going to severely impact this constructed wetland. And then beneficial use protection. So the constructed wetland in Carli Creek itself is actually a migration refuge for a lot of salmonids in the Clackamas River corridor. So when they're coming back from the sea and going up the Clackamas to hatch and rear their young, it's a nice place for them to stop over, and you want to give them, you want to have water and cookies waiting for them when they get into the creek and not something harsh and toxic. Next slide. So what were my research questions? I had two main questions. The first one had to do with the wetland and how well it reduced pollutants, either on a concentration or mass basis, which I'll talk about in a minute. And the other research question had to do with describing its performance or its reduction of pollution in terms of environmental variables like maybe precipitation or constructed wetland variables. And that kind of guided my study design, which I'll talk about next. So we're again here at an aerial view of the constructed wetland. There were 5 monitoring points I chose strategically on this wetland. 3 of them were on the treatment terrace itself. One was representing what came into the terrace. The second one was after the detention pond. The third one was what was coming out of the terrace, so we kind of had a before and after look. There was also 2 points on Carli Creek itself, one upstream of any influence from the terrace and the constructed wetland, and one downstream on Carli Creek. So we could kind of, again, get a before and after of this adjacent creek. I collected 14 separate events, roughly every 2 weeks apart over the course of 6 months. I did the field sampling. This was like my favorite part of the whole project. And I also took precipitation data from a rain gauge we had nearby, and as well as looked at some river flow data because the river was so close to the wetland. I wanted to see if there was any influence from that. So next slide. So installing the equipment, right? You'll see my smiling face, maybe behind the mask. On the left there, that isn't the exact manhole I installed the equipment in, but it's a similar manhole to it. And I was fortunate that one of my monitoring points was piped, so logistically installing a flow sensor at that monitoring point was very simple. Got that installed right away. The other two of my other sites I wanted to get flow data from were open channels, and kind of a simple, straightforward way of determining flow on a creek in an open channel is using the stage discharge relationship. So I installed those there with the help of Jeff Budnick from West Consultants, who is like a river measurement pro, and was very patient as he did most of the hard work, and I just like dug holes for sand and stuff like that. Next slide. So what parameters did I monitor? Similar to those 4 circles I showed back in the conceptual model, I measured in different ways some water quality parameters like pH and temperature, as well as like how much solids were in the stormwater that was flowing out of the MS4 system, as well as 3 different nutrients and a suite of total and dissolved metals, including mercury and copper, like metals we're concerned about in terms of how they affect fish. Next slide. All right, so I said I would talk about this. Concentration-based reduction and mass-based reduction, what does that mean? So concentration-based reduction is just a metric that I chose to use to look at the system's performance. And easiest way to think about it is what comes into that treatment terrace I talked about and what goes out of the terrace. And the percentage difference between those two is what that number represents. So a positive number would indicate that the pollution was reduced. A negative reduction number, which you'll see happened occasionally on this treatment wetland, would mean that it increased from start to finish. Mass is very similar, but mass incorporates flow as an element of the calculation. So if this wetland was designed to infiltrate a lot of water, so only way to really capture that in terms of mass is to use a mass-based calculation like this. So again, it's before and after. The difference between them is the reduction. And log reduction is a common metric used for E. coli performance metrics, just because E. coli concentrations are usually massive numbers. So you want to get a grip on using 10,000 organisms versus 1 organism, something that makes sense. Next slide. I also looked at Oregon water quality criteria to compare some of my metals concentrations in Carli Creek, and I used this international BMP database, which is kind of like a grant-funded study where the database looks at a lot of different BMPs, which are things like rain gardens you see in people's front yards, or the bioretention cells in this project. And they calculate like median effluent concentration, so what kind of pollution is coming out of them. And that's kind of a nice benchmark in context to compare my data with that data. Next slide. This is a map of the rain gauge stations I used. The one that I actually used is that golden one you see there. It's about 4.5 miles away. And there was, fortunately for me, a USGS station just 2 miles downstream on the Clackamas that I also looked at to compare and try to determine if there was any impact on the performance. Next slide. So what did the precipitation look like during my study period? This window you're looking at is the daily precipitation totals for my project site during the 6 months I was out there. I also looked at the gauge record. The gauge didn't have a very long record, only 4 years, which is extremely short for a rain gauge. But I also just showed you up there some daily averages for that 4-year period, as well as monthly averages, so you can see how rainy was it. Was it an exceptionally rainy year? Was it not a very rainy year? The green arrows indicate my events too that I sampled at. And you can see the events sometimes fell on these big storms, and sometimes were in between storms or after long dry periods. So there's a lot of variability in the conditions I was out there in. Next slide. All right, so on to my first question already. Doing field work was, like I said, my favorite part, but then you get mountains and mountains of data and you gotta make sense of it so I can talk about it with everybody and convey information. And I felt a bit fried, like Yoda did down there at the bottom at the end of it, but we're gonna get into data next. And I'm gonna use an analogy, maybe somewhat liberally here, a snow activities analogy. So if there's any snowshoers or skiers out here, get your snowshoes. I'm gonna gas up the car and we're gonna go up to the mountain and I'm gonna talk about my data a bit with you. So next slide. While the car is getting gassed up, I wanna orientate you with how these figures are gonna look in the next several slides you're looking at. So you'll see several panels, and across each row is a different pollutant, and across each column will be a different site. So you'll be seeing concentration data in that format. The bioretention BMP benchmark is in green in the middle site because that represents our bioretention cells. And there'll be some blue dash lines as well to represent median concentrations across the whole study. Next slide. So bunny slopes first. We're gonna start with only one pollutant for you, and that is E. coli. And the best news with E. coli is that the constructive wetland was extremely good at removing E. coli. My data at the bioretention cells were all below the benchmark for the international BMP database. The red lines you see at Site 3 and Site 4 and Site 5 are Oregon water quality criteria, bacteria levels for a single sample grab. So that's an indication that my data indicates that all of my in-stream sites were below Oregon water quality criteria, except that first crazy one at the upstream site, but that got decreased by the time it made it downstream. I also show down there some log reduction numbers, and it's a range over my entire study period. Negative reductions, like I said, would be increases, but all of my negative reductions were extremely small concentrations of E. coli, just going up a hair more, but still staying below the Oregon water quality criteria. On the other end of it, we had some incredible, like 99.9% E. coli reductions during some events. So overall, it was a positive. Next slide. So what mechanisms are at play when E. coli is getting reduced in a constructed wetland? Well, there's a lot of them. There's things like natural sunlight, killing bacteria off. There's predation, other bugs eating bacteria in the water column. Also, I'm not gonna get too much into that. That really wasn't a part of my study, but I just wanna convey the complexity of what was going on. That could be an entirely different grad project. I also wanna compare my data with other studies that have looked at bacteria and constructed wetlands, and my data was in line with what other studies have shown in Australia and Texas for bacteria reductions. Next slide. All right, a little bit more difficult. Green circles, if anyone's a skier or snowboarder. We're gonna look at solids, and solids at my project, I measured 2 fractions and then total solids, which is just supposed to be the combination of both. And there really weren't any total suspended solids in my treatment wetland or in the creek itself. Most of it was total dissolved solids. And there's kind of a reason for that I'm gonna get into in a second, but the important take-home lesson here is that mechanisms that treat total dissolved solids or dissolved fractions of pollutants are gonna matter a lot to reduce stormwater pollution in this system because there's not a lot of total solids in there. So understanding more about that is gonna be important in the future. All right, these next slides get into my second question, which is about trying to explain the variable treatment performance with environmental variables like rainfall. So on the top are concentration-based reductions for my 14 events. And then for a limited set of those 14, mass-based reductions. And the first thing that pops out to me and may to you as well is that the mass-based reductions were generally better for all of my pollutants. Total suspended solids are a lot of those negative bars you see that are below zero being exported, but percent reductions kind of suffer from this problem of anything really small that's increased even just a little bit and it's still really small can be a negative, it looked like a huge export. So if I give you a quarter and I give you another quarter, you just got 100% more money, but you still can't even buy like a McChicken or chicken McNuggets, right? So that you got to take the concentrations in context. Next slide. So why aren't there much solids in the wetland? Well, upstream of the wetland in the piped section of the separate storm sewer system, we installed this giant hydrodynamic separator, which is kind of like a washing machine basin, if you will, where stormwater comes in one side, shoots and spins around really fast. All the solids kind of fall to the bottom and stay there, and then the rest of the water goes back out. So this system, it will be important going forward that this separator device is regularly maintained to continue keeping solids out of the constructed wetland. Next slide. All right, off the green circles onto even more difficult slopes, blue squares, I think is the next one up. Yeah, my wife's saying yes. So these are nutrients, ammonia on the top, reduced form of ammonia, a reduced form of nitrogen, nitrate, nitrite in the middle, and then total phosphorus on the bottom. So nitrate, nitrite was reduced very well on a concentration and a mass basis for this project across the terrace, so between site 1 and 3, I should say, as well as in stream between site 4 and 5. You'll see in the next slide, though, that ammonia had some increases, but I'm showing ammonia and nitrate, nitrite on the same Y scale, so you can see just how low amounts of ammonia we're talking about in this system compared to nitrate. Total phosphorus, there wasn't much interesting going on there. There was that weird anomaly at site 3 at the very end of the sampling season, but that was probably because my strainer fell off, and I think it was sucking up a little bit of solids out of the ground. There was a similar spike in my TSS data, so next slide. All right, again, concentration-based reductions across the top, and mass-based reductions in the middle, precipitation on the bottom. I didn't talk about this before with solids, but with nutrients, there seems to be a little bit more of a pattern with the rainier part of the season in kind of on New Year's, so late December, early January, mid-February. These big rain events and the ground being soaked, there starts to be kind of a decrease in mass-based reductions for like nitrate, nitrite, but it's still positive. And you start to see even some export of nitrate, nitrite, and total phosphorus after that big, crazy, well, not the largest storm, but that mid-February storm. And there'll be some clues to that later, but you guys might think of why that is the case or what happened around that time in 2021 already. Just get your brains thinking. Next slide. So thinking about nitrogen and the mechanisms that are at play in reducing nitrogen or exporting nitrogen. So on the right, you'll see a kind of a conceptual model of nitrate, nitrite being transformed in a kind of a system that involves plants where plants can kind of consume nitrate, nitrite to help them grow. Or nitrate, nitrite can be reduced into ammonia or denitrified, which is when the nitrate, nitrite is turned into a gas and completely released from the system. Special conditions have to be around for that to happen. I also wanted to compare my mass reduction data with other studies that I found in the literature. And for nitrate, nitrite at least, which is shown as NOx up there, it was pretty in line. It was quite aligned with a lot of the other studies as far as studies that reported nitrate, nitrite reductions. Ammonia, on the other hand, like it shows there was not very good retention in the system, but again, we're talking about like really small amounts of ammonia, but worth studying more and understanding. Next slide. Okay, black diamond, metals. I want to talk about metals. We had 3 metals I'm showing you up there: copper, lead, and zinc. Cadmium was a very low concentrations most of the time, so I'm not going to share it. And mercury was also very low, but maybe a result of the method I used. It didn't have a very low detection limit, so can't really talk too much more about that. But again, you'll see the international BMP benchmark bars on site 3. Copper and lead were all well below those benchmark concentrations, but zinc was sort of middle ground, kind of performed almost as well as a lot of other bioretention BMPs. And the curves you see on site 4 and site 5 are the water quality criteria curves for those specific metals. Worth saying is that for copper, in Oregon, they use something that's called a copper BLM model, and it models 11 water quality parameters and creates an instantaneous criteria number. So that's why the curve kind of like wiggles and it's not a straight line like the other criteria were. For every event, there was a different criteria to meet. I didn't measure all 11 of those variables during my project though. So what the model asks you to do is use these protective concentrations for the model to create a criteria number. So all that's to say, these are highly protective criteria values that may be higher if I had measured the actual water quality. The good news is that most of my concentrations for dissolved copper were below those criteria still for copper, except for that first event, again, at the upstream site. Next slide. All right, concentration-based metals reduction looks like a horror movie. A lot of huge negative bars down below, but they're mostly for total lead, and at the end of the season, total copper. Total lead is, my quarter analogy earlier. There's not a lot of lead already in there, so small increases in lead look like huge exports. Not the case. Copper, though, is interesting. It's like something happened in mid-February that caused copper to suddenly start being exported from a concentration basis. Next slide. Mass-based reductions were generally positive, and there's definitely in this figure like a sudden switch. And what happened in mid-February, I've been alluding to the whole time, was that ice storm, where many of you may have been out of power for several days. It was a pretty severe kind of shock to this system. I'm assuming may have had something to do. The only thing I could think of that had something to do with these mass-based reductions becoming so poor at that time, based on precipitation data alone. So it took about 3 or 4 weeks for the system to kind of bounce back from how it was performing before and retaining those metals. So it definitely affected it. Next slide. So like the nutrients slide, like what is affecting metals reduction? Most of the metals in this system are dissolved because of that big washing machine that was installed in the pipes upstream. So, and how do my metal data compare from at least a total fraction with other reported total metals reductions? And my study doesn't look like metals get reduced that well. I'd argue that constructed wetland age has something to do with that, and the fraction of metals has something to do with that. There wasn't a lot of dissolved metal data to look at out there in the literature, but because there's so much dissolved metals in my system, I would be interested in learning more in the future if that would improve at all, or what that might look like. So the next thing is kind of some conditions in the constructed wetland that control how dissolved metals get retained or not. So reducing conditions, when you think about reducing conditions, it'd be like in soil without oxygen, soil that's not being disturbed a lot with heavy flows and rain, and high pHs are conditions that would immobilize certain dissolved metals, help them stick in the system. On the other hand, things like high rainfall, high flows through the constructed wetland would help would help export metals, especially lead. So that's the mechanism I'm thinking is at play here, but it's difficult and it's not something my study looked at. Next slide. So why are these percent mass reductions always so much larger than percent concentration reductions? And the main takeaway and lesson is that there's a lot of infiltration of stormwater happening on that treatment terrace. So like I said in the beginning, mass incorporates a volume element to it. So what I'm showing in this figure is the flow at my site 1 and my site 3 before and after the treatment terrace. And the site 3 is the blue line, which is always lower than the red line, at least at the scale I'm showing. Also, the peaks are smaller, which is important too. So the constructed wetland acts as like a huge sponge, but the sponge, it matters how much water that sponge can absorb depending on how dry it was before and how much room there is for water to actually pool in there. So that's something I thought about a lot while I was doing this project as far as what was controlling how well the volume reductions were happening. Next slide. Okay, getting to the end. Study limitations. There were a lot of things the study didn't do, and some things that could have been done better if I had been wiser, maybe the older Yoda. One of the things was that peak discharge rates I didn't really get a good grasp on. For the open channel sites I had, you need to be out there when it's flowing and ripping through there to really understand how the water depth and the discharge is related to each other. There is a lag that I kind of started picking out when I was looking at the flow data from site 1 and site 3, and that is and the lag is to say that when a huge plug of water comes into the wetland, it takes a couple hours for that plug, the peak of that plug, to come out of the wetland. And that depends a lot, again, on like how wet that sponge is already, how dry that sponge is already. The precipitation record was really short, so maybe it would have seemed like just an average rainy year if I had a longer record to go off of. I didn't target any storms specifically. It was a randomized kind of study design, and storms could be critical periods when the wetland's performing really well or when it's not performing well. Also, like I've said before, the wetland's young. Who knows how the treatment will change? Well, there's some indications of how treatment's affected with age, but it'd be interesting to learn more. And there's several other benefits to constructed wetlands, like habitat provision and vegetation effects, like how dense is vegetation in the wetland, and does that control anything as far as like retaining nitrogen better or reducing ammonia exports. Next slide. All right, so big takeaways. The volume reduction effect on the terrace is extremely important to its performance from a mass perspective, and maintaining that mechanism on the terrace is going to be important to keep pollution from getting out to Carli Creek and Clackamas River down the road. Also, nitrite was really well reduced, oxidized nitrogen, but ammonia was exported every now and then. There seemed to be some explanation given by the rain record as far as nutrients and metals as far as that's concerned. The last thing was that dissolved metals. The dissolved metals are the main fraction in this constructed wetland. So mechanisms that promote retention of dissolved metals, such as like adsorption or precipitation, maybe with other dissolved things in the water, the stormwater runoff, are going to be important. And the couple recommendations I have, I've kind of mentioned them throughout the talk, but to keep nitrogen and phosphorus in the system, one approach in the literature is to do periodic vegetation harvests. That could be something that's effective at this particular constructed wetland, because when plants die and they decompose in systems like this, they have a tendency to export these nitrogen compounds and phosphorus compounds. So once they get cut, you want to take them out of the system. Also, you want to control the capacity of the system to hold that water. You know, if you're thinking of the sponge analogy, you want a big, fat, huge sponge that cleans your car. You don't want a little like sponge that you're cleaning your dishes with. And the last thing is dissolved metals. It's again, anything that promotes dissolved metals retention. So dense macrophytes, dense plants that provide a lot of surface area for either other plants to adhere to those plants on and help catch these dissolved metals floating by, or just kind of provide a better screen. Next slide. This project gave me a lot of new questions I would love to have time to pursue, particularly like what's the dominant mechanism, what is the actual mechanism that's controlling these pollutants in the wetland itself? Also, what differences in time might be happening. So my study period was only during the winter, when it was raining the most. I did that on purpose, but the growing season in the spring and summer could show very different performance for this constructed wetland, and it'd be interesting to learn that too. Next slide. All right, this is the second to last slide. Thank you to so many different people that made this possible. My community partner who took on this project, this wild idea I had at the very beginning, let me work during this project, and I don't know, we're just supportive from the ground up. A water quality lab that tolerated all of my samples I'd bring in and did most of the work for me. They really deserve a lot of credit. They helped do all the analytical methods, and I was just out in the field, listening to birds sing in the morning. The PAN lab group, who watched me present this at varying degrees of completion, like half a dozen times, and were patient and listened to me. PSU professors, they helped me learn this field I hadn't even known about before I started grad school. Funding to present my research at other conferences, family and friends who are here today for driving so far to see me, and of course, Christina, last but not least, for letting me work in my office for hours and hours on end and not bothering me while I worked. Thank you. And that's my presentation. I'll take questions from the Zoom call or anyone in the room, but if you do have a question, just wait for the mic so folks can hear you.
When we have questions online, if anyone would like to raise their hand, I will call on you and allow you to speak in the room so that Chris can hear your question. We have someone, Luke Russell. Luke, please unmute yourself and you can ask your question.
Hello. Hi, Chris. That was a good presentation. I just have one question. I think you mentioned it at the beginning, that the stormwater coming into the area gets split between Carli Creek and the wetland itself. Can you speak to what that partition is? Is it something that's variable, and how is that determined?
Yeah, absolutely. Thanks, Luke, for the question. I'm really regretting I had a slide after my thank you slide that had a picture of that actual partition, and I took it out. So very prescient question. The way that the project was designed to handle that was something called a weir wall down in the pipe itself. So if you picture a storm sewer pipe, big cylinder, and then there's a wall that they built across the bottom of the pipe that has a hole in the bottom. So the wall is designed to let some base flow go through and provide water to the creek at all times of the year. But after a certain point, more of the water is shuttled to the constructed wetland. So it's designed to help pick up these more polluted storms and direct it to the wetland for treatment. But the wall doesn't fill the whole pipe. So at some point during really massive storms, that wall will get overflowed and more water will flow to the creek with less treatment than if it had gone to the wetland. So that's kind of how that's situated. Ian, 1 second though.
You have the separators and it goes into the wetland. Do you have to clean the wetlands out after so many years when they collect all the, whatever?
Yeah. Yeah, there's a lot of research and there's a couple studies in the literature that looked specifically at some wetlands that had no maintenance for up to 16 years even. How well did those perform versus some smaller scale wetlands, bioretention cells that had maintenance, regular maintenance, and how well did those perform? And I would argue that, yes, we should keep an eye on these things. Maybe not perform maintenance without understanding why we're doing it first. But yeah, I think maintaining vegetation, maintaining the sponge so you're not cutting your sponge pieces off over time, and you still have a lot of capacity to store storm flows. It's a tongue twister, is important too. Anything else? Easy? Or tough?
Thanks, Chris. I'll save some harder questions for later, maybe, but you did mention one of the elements of the project was stream restoration itself, actual wood placement in the streams to stabilize some erosion, provide some habitat for fish. And I know your project was mainly looking at the treatment portion of that, but do you have any observations on how those systems are doing, any interactions with Carli Creek and the Clackamas River, and how that may have not only influenced that habitat or the wetland itself? And while you were out there listening to the birds, did you have any other ideas about future studies on that creek restoration itself?
I was out there during some pretty wild and high flows, especially around that huge storm in late December. And the creek did backwater quite a bit, almost all the way up into the channel. And that's, you got to think, it's about 1,500 feet from the mouth of Carli Creek to that backwater channel. And there's maybe 15 feet of elevation drop, so maybe not that much, maybe like 10 feet. But a lot of the large wood that was placed in the middle of the creek is still there and looks like it's in good shape. It's starting to scour how you would think large wood would scour and create like complexity in the channel, which I think is exactly what you want to create a resting place for the water, the milk and cookies you want for the fish as they migrate up the Clackamas. I didn't think too much about future studies within the creek, although it's hard to describe in words like how starkly different that creek looks now with the restoration than before. There were some photos I found where it was just like this like nasty little ditch with like blackberry bushes and reed canary grass growing on the banks and just like no complexity at all. And now with the large wood in there, there's some winding going on and there's a lot of different plants growing. So I think one piece that I didn't really focus on was the backwater channel and the creek itself in terms of habitat complexity or bugs even. I didn't even look at all of the macroinvertebrates in the creek. So looking at that data, because there is a historical record of bug data in the creek prior to the restoration. So how long that might take to rebound, it would be interesting.
I have a couple questions online for you, Chris. First, Jen Morse says, it would be interesting to know what happens in summer with warmer temperatures. Do you think the wetland would be more likely to retain or lose nutrients and metals on a concentration and mass basis?
My first thought is that in the summer, that any nitrogen cycle would be kind of supercharged. I think you'd have fewer, because the water depth would be lower without all the storm flows, you might have more oxygenated water. But that may, at least when I was out there in the winter, there was high DO across the entire terrace. Maybe in the summertime, the DO decreases quite a bit at the end of the terrace where there's not as much flow flying through. So as far as metals though, I would expect metals reductions to be even better, but it'd be tough analysis to do because a lot of the metal delivery is via stormwater runoff, and in the summertime there'd be fewer storms, there'd be less water transporting metals to the wetland. So, but the nutrient question is an important one, and I think it'd be just as interesting to know how it acts in the summer as the winter.
Adam says, thanks, Chris. Can you speak to why you used bioretention rather than constructed wetlands as a baseline comparison? Also, do you or Wes plan to continue water quality monitoring in the future?
To the first question, the main purpose of using bioretention was that the International Stormwater BMP database didn't have a constructed wetland BMP in its database. They considered, actually, if you ever are interested in read that database and the reports they put out, they thought about doing sort of like a whole system performance analysis, but they instead report individual treatment units for green infrastructure like a bioretention cell versus like the system at Carli Creek, where it's really a retention pond first and then a train after it of bioretention cells. So that was the reason why I chose that. And then will Wes continue monitoring it after this? I think I am fortunate to have some say in that because I work for Wes, and I hope to continue doing that, but it will not ultimately be my decision. But I think this is a good start, and it's worth studying something as special and unique like this system.
Eric Jansen says, what are some ways that the community can be more involved or engaged with projects like this? Can you take tours, and or are there any educational signs to help inform the community?
Those are great questions, and I think give me a call and I can give you a tour down there when you want, or anyone else at West would love to walk around and listen to birds sing whenever you want to give us a call. The tricky thing is there's really only public access via the Clackamas River right now, but that could be changing in the future if we can work with some community partners potentially and allow another route on land to get down there. There aren't any interpretive signs yet, but I think Wes has done a pretty good job of promoting this project, and there's a lot of information online, at least, about the project. So I would point you there.
I'll add for him that you can go to Wes at Clackamas.us to look at that website.
Yeah.
Lara Jansen says, great work, Chris. What would be your ideal monitoring plan, broadly speaking, for this Carli Creek site going forward in terms of timing and sampling components? And then I have one more question after that.
Ideal monitoring plan. Ooh, man, if money was no object, right? I think because the flow reduction component is so important to its treatment, based on my study, that getting a handle on the flow moving through the system would be very important, and that is not free. It's not cheap to do that. So I would develop a plan that establishes those open channel sites better and gets a better grasp on flow. Maybe monitor some of those outfalls that supply Carli Creek with separate storm sewer water to get an idea of how the diversion works. And as far as water quality sampling, I'm going to take the easy way out and say my ideal monitoring project would depend on the question you're asking and how you make your study design. So that's that.
John Burns has a very related question. He says, after your experience on this project, and if you had an unlimited budget, what would be the first action you would take to enhance this system?
Oh man, limited budget, first action to take to enhance the system. Wow, I haven't even thought that far ahead. That's a great question. I think that there is a big role, and it was part of the design of the wetland to use these wetland plants, these wetland specific plants that need to be in these environments to do a lot of stormwater treatment. So if budget wasn't an issue, I think we're already doing this for another reason, but I would continue these vegetation surveys and maybe perhaps do some experimentation on maybe different zones in the bioretention cells to see if certain wetland plants in this system, in this climate, perform better at removing pollution than other wetland plants. And that would take some thinking as far as how to set up the experiment and do the sampling itself. But I'm not really a plant biologist, so that would be way out of my wheelhouse. It would take someone with way more plant identification skills than me.
Well, he says, great answer. And we have just posted the link to the Carli Creek project in the chat.
Thank you, everybody. Yeah. So that's my presentation. Any other questions for me on the Zoom or in person? Okay, cool. We'll take a quick break.